In this segment, I want to start getting into antenna design. Now, if this is the first segment that you actually are paying any attention to, I'd highly recommend that you track back a couple of episodes and take a look at the other previous segments I've done about radio connectors and coax. That's very important. Do not just jump straight face first into this. You'll probably fuck something up, and you'll most likely damage something, or just things won't work. The bottom line is you have to have the appropriate coax and appropriate connectors and a device that has those connectors and such. So, past couple of episodes, I've been focusing on how to connect an antenna to your device, how to mod your device, how to get the proper coax, how to crimp stuff. That's over and done with. Let's learn how to make some antennas. But before we can do that, we have to understand some principles of what a radio wave is. So I've got a couple of slides in a presentation here, so let's go ahead to that and I'll try to explain some of the fundamentals. You have to understand that frequency is a measurement of oscillations of a sine wave for every second. Now, a sine wave is an electrical wave that'll actually repeat up and down from a positive to a negative so many times per second. That is what frequency is, how many oscillations per second. Now, you have to understand wavelength. And the wavelength is the distance between two common or similar points on that waveform itself. This little symbol on screen is our friend lambda. And lambda is the Greek character in math for wavelength. Whenever you see this character, it is going to symbolize the equivalent understanding of what your wavelength is. So this means wavelength. Now, to calculate the wavelength, we need to know c, which is the velocity of light, and f, frequency. So, the letter c is going to take place for the velocity of the speed of light, and lowercase f is going to take place for our frequency. So, because we're going to be working a lot in 2.4 gigahertz, we know that the frequency is going to be 2.4 gigahertz, and we know that the speed of light is 29,979,245,800 centimeters per second. So lambda, or wavelength, is equal to c divided by f. So your wavelength is equal to 29,979,245,800 divided by 2,000,000,004,000,000. And when we plug these values in for Wi-Fi, the wavelength comes out to about 12.49 centimeters or 4.9 inches. So there we go. Now we understand what the wavelength is. The wavelength is the actual physical distance between two common points on a sine wave, or on a radio wave. And the reason we need to know this is because our antennas need to be specifically tuned to that wavelength. The reason being is an antenna is essentially a net for radio. So when you have an antenna, when that wavelength changes, when that physical size of that antenna changes, you're also changing in what it actually absorbs on that frequency. So this is how you tune an antenna specifically for a frequency. So, we know what wavelength is, we know what frequency is, and we know the basic concept of what an antenna does, but really, do you understand what an antenna really does? Let's say that this balloon, for a lack of a better example, because I don't feel like spending 3 hours to go and do a computer-generated simulation on a presentation that should only take 15 seconds. Let's say that this little red balloon is a visual representation of your radio field, or your estimated radiated pattern. In the very center of this, right around here, would be your transmitter. What your antenna is basically doing is, it's going to manipulate this field of energy so you either have more or less gain. So, right now we have a perfect sphere. Now in radio this will never happen, this is just for visual sake here. Now, we have an antenna, and let's say today we're going to make some dipoles. And what it's going to do is, it's going to take this ball of energy, this estimated radiated pattern, and it's going to squeeze it. And if you notice, when you squeeze it, the sides squeeze out. Squeeze out of the sides. Same thing, so if we were to go this way, it'd squeeze up. So what the antenna is going to do is, it's going to sacrifice height for distance. So, other types of antennas are like beam or directional antennas. What it'll do is, it'll squeeze the back end. So it'll do that. You notice how you got a nice frontal lobe? Each one of these bubbles are called lobes. And some antennas, what they'll do is they'll squeeze the middle. So by squeezing the middle, the sides stick out. So yeah, you're going to be losing height, or you're going to be losing the direction from one end. But what you're doing is, an antenna is effectively manipulating that field of energy like this balloon is being manipulated by me. So some of the antennas that we'll be eventually designing will actually take the back end of it and do that. But if you design your antenna wrong, well, that's what's going to happen. So, it seems like it's really complicated, but this is just another step of the process. What your antenna is actually doing is, it's taking that field of radiated energy, of radio wave, and it's taking that aura, and it's actually going to mold it and manipulate it into what you need. You can't add energy, you can remove it, but that's kind of defeats the purpose of this. See, people actually think that just because you add an antenna to something means you're going to get better range. Or some other people think that just because you increase your power output means you're going to broadcast further. To be all honest, a good antenna is usually more important than really strong power output, because if your antenna isn't pushing out that signal where you want it, or if it's not tuned properly, it's not going to work. So, let's go to the table side, and I'll get to building our first antenna called a dipole. Now, a dipole is an antenna like a pole. You know, you have a positive and a negative. Dipole means you just have two sides. And in a previous segment, when I was doing Introduction to Radio and Radio Scanners, I explained dipoles and beam antennas and things of the such, so you might want to go back a bunch of episodes and check that out. So let's go to the table side, and let's start putting stuff together. Before we begin, I want to analyze a couple of commonly found dipole antennas that we have in our 2.4 GHz products. The first thing I want to show is, we all seen these little default antennas that come with your router. These are called rubber duck antennas, oftentimes because the rubber that they're made out of are often used in the bath time rubber duckies that you find in pedophile rape kits. It's got a standard reverse polarity SMA connector, and inside of this is a typical dipole. Now, we all know from experience that these aren't the best antennas to deal with, but do you really know why? And I've got a couple more antennas that are similar to this, and we'll actually explore that fact before we get into anything. Now, we've also got the antenna that I removed from the USB Wi-Fi card from a couple of segments ago. For the sake of learning and understanding, I decided to put the antenna on the sacrifice block, and I cannibalized it for you guys. This is the antenna. It's just a circuit board. Nothing more, nothing less. Not very complicated. And the third product that I decided to go and pillage and destroy and make look fugly as all hell for you guys is my 2.4 GHz security camera. If you've noticed that this antenna is nothing more than, quite literally, the shield has been stripped away from the signal conductor, and then a tube has been soldered onto the shield end on exact wavelength, or I should say size. So I take my compass, and using it kind of like a caliper, I've measured this, and it turns out to be 2.5 centimeters on both sides. So we got 2.5 centimeters here and 2.5 centimeters there. And doing some math on the wavelength, 2.5 centimeters should come out to about 1/4 wavelength on each side. So this side is quarter wavelength, and this side is quarter wavelength of 2.4 gigahertz. And if you expand them both together, that means this is a half wave dipole, because we have 1/4 on each end. Now, you might be asking yourself, well, if that's the case, why can't I make a 2-wave dipole? And the reason being is because you have to remember, when you change the length of the wire, you're changing the offset frequency. You're changing the frequency that it can receive. So if this was excessively long, like if it came out to here, well, not only would it be really bulky and, you know, disgusting looking, but it would also pick up a different frequency. So you have to make sure that your antenna is properly tuned to the frequency that you're picking up. So if we were to, on average, a full wavelength of 2.4 gigahertz is almost 5 inches. So if you have one wavelength on each side, that'd be a full wavelength dipole, but that could also change. You could also be picking up spurious frequencies across other bands. So this is usually why you keep things as specific to the frequency as possible. And this is also why you can't just get like a 30-foot long piece of wire, attach it to your Wi-Fi card, and get all of the signals in the neighborhood. Okay, this little bugger. When I measure this, it came out to be 2.5 centimeters as well, which means that little circuit board, yep, 2.5 centimeters. This little circuit board has 2.5 centimeters on it on each side, and that creates a half-wave dipole. Yay. Why are we using half-wave? Why can't we make something better? But a lot of times half-wave works just fine. Now, if you wanted to make one, the first thing you're going to need to do is, of course, as always, make sure you have the appropriate coax. Reverse polarity SMA going into, I forget what kind of coax. I sacrificed this off of a really crappy antenna. Now, we're going to copy the design that these guys are using. So we're going to need some kind of tubing or some kind of pipe. And this is going to actually fit down the center of this. And then we're going to solder a length of wire out of the top. Now, I got that tube from an old antenna, an old TV antenna. Oh, go away, balloon. Remember the old rabbit ear antennas for TV, for broadcast TV? Well, of course, you can't use this antenna as is. So what I did was I extended it, and I just cut a segment out. And that's where this tube came from. This literally came from a leg of an old TV antenna. Now, you might actually have something else laying around the house. Like you can actually go to the hardware store and you can buy a brass tube. This tube actually has the exact outer diameter and inner diameter, so you can actually feed LMR 195 coax down this hole. So this would be good for a really nice, sturdy antenna. So, we've got the antenna and I've marked 2.5 centimeters. As for the actual wire itself, any wire, here's some household power cable that I pulled out of the garbage. I pulled the sheathing off of it just so I can solder it. You can use an old coat hanger. Here's a small length of coat hanger. Just something metal, something conductive, and something you can solder to. So, I'm going to use a very little saw. Got a little miter saw here. I got it from the dollar store for $1 with a couple of extra blades. And I've marked 2.5 centimeters, and I'm going to go ahead and I'm going to go and saw this off to the proper length. It took a little bit of effort, not really, but for the sake of just bitching and complaining. Anyway, here we go, got our marker. I'm going to go and mark up 2.5 centimeters. 2.5 centimeters. Okay. And then we're going to take some wire cutters. I've already pre-tinned this wire just for the time constraints. We're going to cut this wire. Now, whenever you're making something for 2.4 gigahertz, try to stay as spot on to your measurements as possible. So, having a hand file around and actually filing down things down to the closest millimeter is a good idea. Personally, I tried to be less than half a millimeter off, but if you are, it's really not going to kill you. It could kill your Wi-Fi card, but that's besides the point. Okay, so we got the tube end and we've got the little nubbin end. So let's go ahead and get this on the coax. Got a little razor blade here, and I'm just going to pull off this outer insulator to reveal the shield, trying very carefully not to actually pierce the shield or even the center conductor, and then just peel the shield. Well, actually, first thing you got to do, I always forget to do this. go ahead and put your collar on first. Go ahead and put the bottom half of your dipole on. And we're just going to go and mangle this as much as we can. And there we go. We just want it going in the opposite direction. Just like that. And then we're going to reveal some of the center conductor. Like so. Now I'm going to reposition my camera. We'll go to the desk clamp side so you can see me soldering this. Here we have the bottom half of the dipole locked firmly in the clamp. And you know what? I retract my statement earlier. It is actually easier to put this bottom half on after you've pulled all of this back. Once you pull all of the shielding back, feed this through the neck and out the top. And you can expose this a little bit. And taking the soldering iron and some solder, try to get this affixed. But remember, don't use an excessive amount of heat. You don't want to melt any of the important stuff on the inside, and you especially don't want to ground anything. So you don't need an excessive amount of solder. Just get it affixed into place nicely. There we go. It's not too hard. Kind of like spot soldering, you know, instead of just blobbing it on and going ape shit, just heat it up a little bit, apply a bit of solder, and just let it flow. There we go. That's going on nicely. There we go. So, make sure we get that nice and shielded up. It doesn't have to be super perfect. So, alright. Not excessively difficult. Okay, I'm going to let this cool down a little bit before we go to the next stage. Okay. And of course, as always, pre-tin. Pre-tin. Tell you the truth, we don't even need to really do anything. As long as this little wire, the shield, the signal wire, is 2.5 centimeters, then we really don't even have to do anything. But to tell you the truth, I want a slightly more sturdy wire than this really flimsy coax. I'm going to trim this down. That's an excessive amount. Okay. And, you know, here we go. Here's our little signal wire. I'll try to do this on frame. This is actually very awkward for me. So, you'll have to forgive me if I block anything. There we go. Not the prettiest solder job in the world, but it'll work. There we go. We have a nice little itty-bitty dipole. But it's unprotected. Any of the elements can destroy this. I mean, even my fingers are throwing all of that off. So, I thought of something really, really ghetto-tastic. Took an old pen. Literally, it's just an old clicker pen. Pen. Hi, I'm a pen. There you go. You can cut the pen to size. A lot of pens usually have that nice little ass end cap. You throw this in, spooge some hot glue in the ass end, or whatever, and you get yourself a nice little detachable dipole. And if you can go get your ass to the hardware store, you can go and get these little itty bitty clamps. So now you can actually go around. You can go ahead and glue your dipole, and you can actually have a clamp-on dipole. So if you take mass transit a lot or in a car a lot, when you're inside of a car or a train, they're made out of metal. And as we all know, hopefully from earlier segments if I've explained, metal will reflect radio waves. So if you're inside of a metal car, or if you're inside of a metal train, your radio signal can't get outside. So by taking this and just clipping it outside, well, you have an antenna outside. Now you can actually propagate your signal a little bit better. Okay, for quality's sake, I'm going to be listening to this access point for a little bit, and it's got the stock and standard rubber duck antenna. And what we have done is pretty much create an exact copy of that antenna. So there should be no reason that our antenna operates any poorly than the other one. So let me go and signal Bunny, and what I'm going to tell her to do is unplug that antenna and switch it out. Alright, and notice how we have no signal. She's swapping out the antenna. Alright, seems like she's starting to plug the damn thing in. There it goes. So it goes to show you that the antenna that we've created, now of course this access point is clear across my house, in my lab, cutting through 2 walls, and as you can hear from NetStumbler going off every 2 seconds, I've got currently 9 active access points that are interfering with me. So, it goes to show you that the antenna that we created is just as good as a rubber duck. However, because it's on the end of a cable and we can put this outside of our window or outside of a vehicle, this antenna is actually better than, in its features, better than an original one. I decided to fashion a dipole with the arms being 3/4 wavelength, 91 millimeters, and look at that. We've got quite a bit of difference. So we went from an itty-bitty, inky-dinky little dipole to something that's slightly bigger. So it goes to show you now, if we were to make this a full wavelength, yeah, it would be almost 10 inches long, but still, you'd have a significant amount more gain. So it goes to show that just with a little bit of wire, a piece of coax, and an appropriate connector, you can go ahead and make yourself a better antenna than what those stupid little rubber ducks have. If not the same amount of gain, then maybe you get a little bit more. And if you notice that now that I've had this new antenna, there aren't as many gaps in the radio signal. So really when you're making an antenna, you're not just increasing or decreasing the signal strength itself, you're also increasing the link quality. You're making it so there's no more gaps and no more breaks. So this is just the first part in a multi-part series, so if there's any questions or comments, or if you have anything that you need to ask or would like to say, I know that I didn't cover everything, there's always the next episode. So, go out, enjoy yourself, have fun, and I'm surprised that actually just shot up so much. Wow. That is mighty nice. Can you believe that I made this out of crap I made this out of garbage? Huh. Anyway, end of the segment. Have fun, everyone.
Hey everybody, I'm Dortz, and this is the C++ tutorial on arrays and searching. So, in here, I'm going to cover the basics of big O notation, arrays, pseudo-random numbers, sorting algorithms, and searching algorithms. And I also got to apologize for my sound. It seems like I've moved my recording studio to a cave. But, so, for this tutorial I included a few more libraries: time, SDDLIB, standard library, and CONIO, which is console I/O. And time in the standard library is what we need for random numbers and the time function, which we'll get to when we cover pseudo-random. And with CONIO we need getch, and that's for only if you're running under a GUI. This is going to keep that window from immediately closing, so you just add it at the end before you dump out a main. All it does is it waits for keyboard input of any kind. So, first, big O notation. For algorithms, it's designed to actually tell us about how fast an algorithm's going to run, but generically big O is used to find a function that's always going to be bigger. So like if we have f of x is x times c, and c is guaranteed to be less than x, our obvious big O is x squared. So in algorithms, it's going to be the maximum and average time for a specific algorithm to run. Now we aren't going to measure algorithm times in seconds because no computer is the same and everything's going to run at different speeds. Instead, the effectiveness of an algorithm is measured by how many times it needs to run or compare values. So usually that's in a standard of n, which is the amount of data being sorted, or for our purposes, the size of the array. And so if it's big O n, it's running in big O n time. So the algorithm's going to do n comparisons before it finishes. So, perspective. N squared, very inefficient. It's going to take n comparisons, and it's going to run through all of those comparisons n minus 1 times. Like a while loop running, and each time it runs, it's going to do n times. So n log n is taking log n runs and n comparisons. N is just going straight through the array, comparing each value. And I'll get to arrays in a minute. And log n is going to cut it in half until you have only one value. Now we're going to see just these 4 numbers when I do big O, and these will just be the definition of the worst case or average case for all of the algorithms I'm going to show. So, obviously there's other parts to algorithms. It's swapping time usually is going to be a factor. I mean, in modern computers, it's basically free time. Theoretically, it is, but, you know, again, modern computers, it's going to do, like, no time with swapping. It's going to be a small constant. So we can just about ignore it for most, except in cases where we can't. So, like with EEPROM or flash memory, that's going to take an insane amount of time to run even efficient algorithms here like quicksort. So I have a sort that I'm going to show you that solves that swapping problem. So I'm going to jump right into the explanation of what I'm going to show you. First, bubble sort. It's a bad algorithm, but, well, it's used to introduce sorting because it's very simple to understand. So it's going to take element 1, and then take element 2, compare them, and then swap them if necessary. So the worst case is going to be where it's going to take n squared comparisons and swaps, which, like I said before, is bad. Selection sort fixes that swapping issue. It's still going to do n squared comparisons, but the worst case is only big O n. And that's very good for if you have problems with swap speeds. And the updated selection sort is cocktail sort, which I'm not showing, but it's basically the same thing, except it grabs a max and a min. Funny thing here, it ends up taking the same amount of time because it's just doing double the comparisons and double the swaps for each run of the algorithm. Quicksort. General, it's basically the best simple sort you can do. It's fast, elegant, implemented with simple arrays. Bubble sort generally takes n squared time, and so does quicksort. And that's only in the worst case. But for the best case, it's going to run in n log n time. And it's really actually easy to hit this specific value. And I'm going to actually show you how to get near that time and even be able to beat it. But I'm not going to go over that until the show notes. But the key element with quicksort is the recursive step. So, back when I was first learning this, my professor described recursion basically like a bunch of desk clerks. Each one does a little bit of the work and then passes the rest of it off to another step to finish it. So, in practice, recursion is basically a function that has to call itself with modified parameters. So in the specific example of quicksort, the work of one clerk is just going to take a pivot point, which I'm selecting right at the head. It's not very efficient, but the partition function that you might write would be very efficient at this because this is the key for it. It's going to take that pivot point and then compare all the values in the array that clerk gets, and then split the array in two and hand the rest of the array off. So one clerk passes it off to two other clerks. One clerk has the lower end of the values, one clerk has the higher end of the values, and they actually have half the actual workload, and they sort their parts, break it in, and send it off. And so it'll keep doing this until they get down to one value and can't pass it away. And then the algorithm's going to kick out. So when you think about it, it's going to guarantee that the array is going to be sorted because the last set of clerks are only going to get one number and they can't pass it along. They have nothing to sort, therefore they can guarantee that their array is sorted because it's only one element long. So, on the two searching algorithms I'm going to show, linear search, straightforward brute force search. It's going to take big O n time, where it's just at the end of the array that it's searching for, or like when it doesn't find anything. So the next is far more elegant, called binary search. I wrote in two implementations, but I'm only going to use the second, a recursive definition of it. And remember before I called these overloaded, and this is different types and different parameters. So, main function. First thing we see, an array of 1,000 elements. Yay, an array. It's the simplest of all the data structures. It just makes a list of n elements. So I'm only going to be using integer-based elements, but again, with the type, you can do just about anything. So when I'm declaring it exactly like this, it's going to build it into what's called stack memory. For any purpose that you have for it, it's memory managed by the system. But if I was going to dynamically allocate it, I would do this, where I'm declaring a new pointer x and assigning a new integer array of size. And that's going to be the runtime specific size. It can be user defined or whatever. And this is of course assuming size is an integer. The memory accessed like this is going to be put into heap memory. That's the same memory, like I said before, that's used by pointers. Or maybe I didn't say it before. But it's dynamically allocated pointers will set up into heap memory like that. So, again, essentially the same thing, because even up here, ARR is used as a pointer to the array. So if we saw up here, when we're passing the array, we use these brackets. We could pass it by reference, but then we'd only be passing the first element of the array. Here, it's telling the compiler to know that there is a full array attached to the pointer we're sending it. The same thing happens when we're deleting too. If we dynamically allocate our array, then we are in control of the memory that it holds. So if we print x, like the dereference x, it's going to print the first element of the array, same way as the pointer. Whereas if we delete x, it's going to delete the head of the array, and it's still going to keep the rest of it allocated, which is a problem because that's going to be just a major memory leak, because we can't release any of that. So we have to delete, tell it it's an array x. Not enough of that. We're also going to use a copy of the array for continuity purposes. Make sure that we have the same composition for each sort to demonstrate how fast they run. So, pseudo-random numbers. Not really random, pseudo-random. They are based off of a set algorithm, but for our needs, decently random set of numbers is fine. Here we have to use a seed, which is like a starting point for the algorithm, and the way we do that is usually with the system time, and for other purposes like cryptography it is absolute shit, but when we just need a chunk of data, this is perfect. Now srand, set random number generator, or seed random number generator, unsigned time. Now this time 0 is going to go to time, and this function returns an integer. And we want this integer cast as unsigned, because it'll return negative or positive, just it's going to overload by the system time because it's a number of seconds since some time in the past. and this is going to unsign that, so it's going to be from 0 to 65,000 something, and then it's going to get that number into srand, and it's going to take that number and it'll give us our seed. Now if I wasn't going to seed this, every time I called rand, it would set the default seed and I'd get the exact same number of random, the exact same set of random numbers each time. And that's, well, basically useless. So here we have how we're going to fill our array. Referencing array is very simple. We use the name of the array, bracket, index number of a value that we want to access, close bracket. Now the indexes for arrays start at 0 and go to 1 minus the size of the array. Here we have 1,000. This is going to run from 0 to 999 and then kick out. Can't access 1,000, that's the termination character for the array. So it's going to take every element of the array, grab a random number, modulus 51. And that's from 0 to 999. So what is modulus? If I didn't describe it before, it's that percent sign, and it's the remainder of. So 3 modulus 2 is 1, 51 modulus 51 is 0, 80 modulus 51 is 29. So our random number modulus 51 is going to give us a set of numbers from 0 to 51 and fill each number into one element of our 1,000 element array. So first thing we do before we run off, we're going to copy the array, and then each time we run a sort, we recopy it. But let's jump into the actual sorts, because that's pretty simple. Alright, void bubble sort int array, and it is denoted as an array, remember. So as previously stated, bubble sort's a very inefficient program. For bubble sort and the next one, selection sort, I'm going to be running both tries and swaps to show you the difference between the two. And we have a temp variable here that is used just for swapping, and a bool variable to keep it in the while loop while we haven't finished swapping yet. So while swapped is going to run until we don't have any more swaps. First thing it does is set the swap false, and it hits a for loop. This for loop is from 0 to 999. I have it 999 because here our comparison statement is going to access the current number, the current index, and the next index. So if I had it to 1,000, when I hit 999, it would index 999 and then segfault and die, because it's referencing the termination character. So each time we do a comparison, we up the tries, and if it is swapped, we up the swaps, and we flag swapped. And swapping is simple. Element 1 goes into the temp, element 2 goes into element 1, temp goes into element 2. Then we have a kick out of how much it takes. Selection sort. This one uses a pretty basic implementation of a nested for loop, and this is going to make it take n minus 1 times, and each run of it sets the minimum as the index that we have, which would be the first time we'd have it at 0, and then it's going to go through the entire array testing everything against our index, our minimum value. Then if it does find something that's less than, we reset it and set our index to that. So then afterwards we check if we have changed our min, and if we have, we'll swap it out and up the swaps. Now the beautiful thing about this, the maximum swaps is big O n, remember, because it's only doing one swap per full run of the for loop at max. Now for the fun part, quicksort. Remember I said it's recursive, and here's the pivot value and some left and right placeholders. And I'll show the pivot value and the left and right holders. They have big importance in a minute. So the first thing, we set our pivot to the leftmost part of the array, which is called numbers, remember, and we have a left and right parameter. So while we still have numbers to be looked through, it's going to hit another while loop that increments it backwards from the right to make sure that all, any numbers that are greater than the pivot are, until it doesn't. And then if we go all the way through and left is now equal to right, then we're done. We've sorted all the numbers. Otherwise, we're going to move our current number over onto the left, because we already know that it's less, and bump left up. So now we have the next while loop moves it left, and it keeps checking that the values are less than and incrementing left. And then it's going to kick out. If it's not equal, it switches back, pushes right back one, and then it's going to jump back to the top of the while loop up here. And it's going to check and make sure that they're not equal accidentally, and it's going to run through again and again until they've finished the first round of sorting. And this will take n time and a certain number of swaps. So then we reestablish the pivot point on the left and reset our new pivot point to the index of the left value, reset the index up to the left, reset the index to the right, and now we're in the recursive step. Remember, each time there are two recursive steps. First, it checks that the left side is not at the extreme pivot side, and then we check the right side is not at the extreme pivot side. And each time, we're going to make a call to quicksort if that's not the case. With the original array, our new left, and the pivot for the left side, and the same left and the same right, and the new pivot for the right. Remember now it's pivot 1. On the second run, for the guy who has to sort the right side, his left, right here, is just to the right of the original pivot point. Now remember, now the original pivot value, is now at a different index point that's sorted, well, partially sorted. All the values on the left of the pivot point are going to be less. And in here, all the values on the right of the pivot point are going to be greater. More on quicksort and possibly how to make it better in the show notes again. So, linear search. I really don't need to explain this, or I shouldn't need to. If you have any questions, shoot yourself. Binary search. This one is a non-recursive implementation that I'm just including to demonstrate the differences between recursive and non-recursive. So, binary search. We have our array, a left, a right, and a key. The key is the value we're searching for. Left and right would be the same thing as before with quicksort, which is just the left and right bounds of it. So it's going to check, make sure that we're running all the way up until the array is of length 1, and then we set our midpoint, which would be just right in between our entirely sorted array, which is very important, and we check it, and if it is, we return it, we found it, and that's midpoint is the index value, that's what it's going to return, and otherwise it's going to call itself on the left. Remember, we have to have a return value of int, so we are returning the value that this would give us. Now, I guess you can understand it as, each courier or desk clerk needs to reply back to everybody else. And well, actually, I guess that analogy kind of works, because each time we go further and further down into the recursive steps, once it's done, it's like, okay, I've got it. Let's return this value. So okay, we've got this, so we're going to return this value, which returns from here. Now, if none of these find it, then every last one of them is going to return -1. So as a whole, it's going to fill up and return -1. So that's it, I guess. The code compiles properly. I have tested it, but I'm not going to show that right now. But I'm going to have some sample output and just a whole ton of more information in the show notes. So hit me up on IRC if you have any specific questions, and later.
Alright, today we're going to do some PlayStation 2 soft modding. Now before we begin, I have to explain that I absolutely hate the PlayStation 2 soft mods. I think they're clunky, unreliable, and they're just a pain in the ass to get working. Now, we've done soft mods in the past for the Xbox and the GameCube, and slightly for the Wii. So you should understand by now how a soft mod works is it actually takes advantage of a flaw in the actual operating system of the console to allow us to load our own rogue code that lets us do other things than play games, or possibly bootleg games. Now, in the PlayStation 2, there was a flaw found in how the PlayStation 1 games actually load. And this allows us to access our memory card to load our exploit, and in which can load alternate software. So for a soft mod, you're going to need an original PlayStation 1 game. And in this case, I have Final Fantasy VII. Not that I've played it, I just have it. You're also going to need at least one PlayStation 2 memory card with at least 1 megabyte of free space. Me personally, I don't mix up my homebrew cards with the actual cards I use for my games, because you have a tendency of breaking things and you don't want to lose all your saved games. Now with any soft mod, you're going to need a way to put the actual exploit on the memory card, and this is where things will always get complicated. Now back in the day, there was something called the Game Shark Save Manager. It comes with this little dongle that you put, you plug a USB cable into the PlayStation, you plug it into here, and then another USB cable into your computer. And this will allow you to take save files from your PC and put them onto the PS2, and then also take them off. There are also other commercial products like the Action Replay Max Media Center or something like that. There's also the Action Replay Memory Max, which is what I'll be using today. There's also the Code Breaker. There are a couple of commercial products which will allow you to take that save file from your computer and put it onto your memory card, which is going to be absolutely necessary. Now there are actual official products like Swap Magic, and Swap Magic is an official disk that you can buy off the internet. And you put it in, and then you can actually put in your backup disks or your homebrew. Whether that's legal, I'm not all too sure. It could be constituted as a crime in some countries or in some states. I don't know. But there's also the HD loader. HD loader is actually kind of shunned in the PlayStation 2 homebrew scene because its intent is to allow you to copy your games to a hard drive. If you have the PlayStation 2 network adapter, it actually has an IDE interface with a Molex power connector. So if you have a drive that'll fit, you can plug it into your PS2. Unfortunately, Sony was kind of a douchebag, and they made it so you can only use the Sony PlayStation 2 hard drive. But using HD loader, you can use a USB drive or any IDE hard drive that'll fit. So a lot of times you'll actually see me with this on the back of my PS2 with anywhere from 4 to 8 gigs in it for a homebrew. Now, if you're going to be playing bootleg games from this, if you're looking for piracy means, expect to be completely disrespected and shunned part of the community. We do not condone this. So that's all I'm really going to get into that. Not condoning piracy here, but making copies of your own games, do as you wish, I don't care. In my honest opinion, I would go with a hard mod for the PS2 any day over a soft mod. I really hate them on the PS2. So, we're going to have to go to the PC side, and we're going to have to get the save file from the computer to the actual PlayStation 2. So let's go ahead and I'll show you how to do that. The first thing you want to do is get your butt over to ps2dev.org. Now, in their loaders section of their website, they have the PS2 exploit made easy. And you're going to have to go ahead and download this. Extract it to whatever folder on your computer, and you'll notice you'll have a whole bunch of files. You'll have something called BA data and BE data. Now the first thing that you really should do is go to the README file. And the README file clearly explains step-by-step instructions of how the exploit works, what exactly it's doing, and its discrepancies. So it's going to tell you that you're going to need some kind of USB thumb drive. In my case, I'm using an SD card that's going to be put into a USB adapter. It's going to explain that if you have a Europe or a UK version of the PS2, you're going to have to copy over the BE data system files. If you have a USA system or an American system, you need the BA data files. So we're going to go over and we're going to copy over the BA data system files. Now depending on which way you're going to get it, like I'm using the Action Replay Max, so I'm going to need the Max files. But, just in case, we're going to copy everything over anyway. So we're just going to send this straight to my removable card. And there's also games-us and games-eu.txt. Now, the reason they have this is, they got the formatting all messed up. Go away. The reason for this is going to have a list of every single compatible game that they've included with this. Now the way this exploit works is when you actually put the game, the PlayStation 1 game, inside your PlayStation 2, it's going to read the product code. In this case it's going to start with SCUS. I think Europe will start with SCEU. And once it reads that actual serial number, it's going to try to load inside of title.db. It's actually going to run the exploit, and it's going to crash into our memory card loader and then load up PS2 menu. So with other homebrew, you can quite literally make it where when you put in this PlayStation 1 game, it'll actually load the homebrew rather than the game. So if you don't want PS2 menu or any other disk loader, it'll go ahead and load whatever homebrew that you want. I'm not going to get into the discrepancies of this. I'll put a lot of links in the show notes explaining different processes and different homebrew that you can actually load on the PS2. Now that we've got the files over on our removable drive, we're going to go to the PlayStation side. We're going to extract this to the memory card. I've gone ahead and I put my Dialup Max Memory original disc in, a Sony PlayStation 2 8 meg memory card in memory card slot 1, and my thumb drive in the USB port. Now I can't exactly explain how to use your specific product. That's something you're going to have to figure out for yourself. It does take a little bit of trial and error, but really just read the manual and you should be just fine. So I'm going to go into the memory card. I'm going to make sure that I'm going to delete the system configuration, because this is where all of the settings are going to reside. This is where the exploit's going to take its home. So, gone ahead and we deleted, like there's nothing on the card now. Now we're going to switch over to the USB thumb drive, and we're going to tell it to copy the system configuration data. Now instead of copying it, what I'm going to do is I'm going to uncrush it to memory card 1. Now this is just the process for the Max memory device. Your device may vary. Right now it's going to read all of that compressed data from the actual file on the SD card, and it's going to copy it all over to the memory card, and that's where all of our you can actually copy your homebrew over to the actual memory card and boot from there, but with only 8 megs to work with, it's really not much when you have some beefy media players or emulation or things of the such. Now that that's copied over, I'm going to go back and I'm going to verify that it's there. And look, if you notice, we have your system configuration, and it takes up 623K of memory. So normally it should only take up, I think, maybe 128K or even less. So this just goes to show that within this system configuration, we have the entire exploit and the trigger, which is actually tailored to work with Final Fantasy VII. Let's go to the PS2 side and we'll trigger the softmod. So we've copied everything out to the memory card. We've got the PS2 and Final Fantasy VII. We're just going to go ahead and put in our original PlayStation 1 game, and we're going to load this up. Now you have to understand that just like many other consoles, that the PlayStation 2 cannot read regular PC formatted disk. It uses something called UMCDR. If you actually read the documentation to the PlayStation 2 exploit made easy, then you'll understand a little bit more. You need a special tool to go and create custom disks that the PlayStation 2 can read. So, as we can notice from the screen over here, that instead of Final Fantasy loading, it actually triggered the exploit that's on the memory card, and here is Adam and Tom's HDD menu, or PS2 menu. And from here we can actually explore the file system, and of course, as always, whenever you're going to do anything, read the help file. Don't assume I know everything. So, we can hit the select button and we can have some basic menu options for moving files around, copying files around. So, if you go ahead and use the PS2 CD Gen, what the hell ever, I'll put it in the show notes. I can't remember the specific name, but it's a special tool specifically custom written to make PlayStation 2 formatted discs. What you can use a standard CDR disc or DVD or whatever your PS2 can read, and you can put all your homebrew on there, and you can create system.cnf files that'll actually install your homebrew to your memory card. Now, like I said, if you have the broadband adapter, you can actually bring this up where you can read from the actual hard drive. You can read from a network, meaning you can stream files over the PS2 so you don't even have to make and keep burning a whole bunch of coaster CDs, because I'm going to tell you right now, you're going to go through a crap load of coasters doing PS2 homebrew. I absolutely hate it. I'd much rather just put the files on the hard drive using the network and FTP, or quite literally just using a USB thumb drive. You can also browse the actual CD. And right now we actually have the PlayStation 1 game, Final Fantasy VII, of course. And there's our system CNF that is actually used to actually boot the game. You know I've left a lot out. I gotta kind of cut this short, but I'll put a lot into the show notes so you can understand. There's really a lot to this. I would much prefer to go in and do this the soft mod by hand rather than using the PS2 dev made easy soft mod. Mainly because I can include whatever software that I want, and I can put the custom configurations to my liking. But if you don't know anything about soft mods, if you don't know anything about PS2 homebrew, and you really just want to get started with this, this is the easiest way to go. So, hit the show notes. They're on the forums, as always. We've also got IRC up and going. And remember, Google is your friend. I am not.
I am the Ophidian, and today I am going to show you about this little device right here. This is called the Y-Spy. It is a poor man's 2.4 gigahertz spectrum analyzer. This in a computer can take the place of a $10,000 piece of equipment depending upon what your needs are. 2.4 gigahertz is a very popular unlicensed radio spectrum, unlicensed set of radio frequencies, if you will. Very common today, used by wireless networks. This happens to be a Netgear Wi-Fi USB stick, used for Bluetooth, like for headsets for cell phones and whatnot. There is also, it's used for security cameras, some of your cheaper security cameras that you can get through Radio Shack, Walmart, that sort of thing. In use for quite a few things today. And what I'm going to do is show you how you can use this device to view and see how much of activity is going on in your neck of the woods on that operating, or on those operating frequencies. So we're going to go ahead and jump over to the software that goes along with this. On Windows, that software is called Channelizer. There are third-party software programs equivalent to Channelizer available for Linux and for the Mac. Those will be linked to. I will try to provide some links for that to add to the show notes, and also to put at the end of the segment so that you can, if you get one of these, you know where to go and get the software for it. These are available for about $100 or so on various places on the internet. They do have a new version of this out that actually has, this version has an antenna built in. They have a new version that has an RPSMA connector so that you can just go ahead and attach your own antenna to it. The other option you have, you could mod this following one of Fox's segments from a previous episode. I'm not going to do that to mine, however. I'm going to leave it intact just how it is, because for my purposes, this way works just fine. So we're going to go ahead and switch over to the Channelizer software running on a Windows machine, and I'll show you what this thing actually does and how this thing can help you if you're trying to track down an interference issue. This is Channelizer. I have the About Channelizer screen up, as you can see. It was made by MetaGeek, available at metageek.net. Go ahead and close that. This is the main Channelizer view. Normally there are three graphs that you can look at: the spectral view, the topographical view, and the planar view. We don't really care about the topographical view. It is interesting information, but it is not really that pertinent to what I'm going to be showing you today. So I'll just go ahead and give you a brief rundown of what the different views actually are. We'll start with this bottom view. This is called the planar view. You have a green bar on the bottom, you have a blue outline here, and then you have this red line that's jumping around. The red line that's jumping around is going through and showing you what the current readings are for that column of data. The way that the Y-Spy and this software operates is it goes through a sweep, and a sweep is a pass from here to here. And in that sweep, what it's doing is it's tuning the Y-Spy to a specific frequency, and then it's asking, what does the Y-Spy hear signal strength-wise? So do we hear a strong signal? Do we hear a weak signal? Then it tunes it to the next frequency, which is another column on here, and it does the same thing again. And it does that through its entire range here, and we call that a sweep. So what you see here, this red line, are the actual results of the current running sweep. What you see in blue is the maximum value that was seen at the time for that specific column. So right here, this was a peak. That's the maximum value that has been seen for this frequency, which is right at around 2.432, somewhere in there, gigahertz. Or over here, where we have obviously a lot of activity, we have a lot of the peaks. Down here where the center of it is around 241.2 or so, showing you the maximum values there. And then we've got some other activity here. This upper view is a history view of that red line. So I can see this line here, this represents 5 seconds ago. This line here represents 10 seconds ago. And this line here represents 15, etc. You can control exactly what they mean by sliding this slider around. But for now, we're just going to go ahead and leave them as is on the default, which is 5 seconds for this space right here. Now, this is showing you a history. This is saying 5 seconds ago, this is what the picture looked like. Then 10 seconds ago, that's what the picture looked like. So you can see kind of over time the different shapes being created by the wireless signals that are in your area. This area here, I'll go ahead and tell you, is my access point. This area here is my neighbor's access point across the street. I have the Y-Spy currently attached to a swing arm. It's actually a swing arm for a lamp, but I've basically got the Y-Spy with some elevation so that it can very clearly see and hear the neighbor's access point across the way. Plus the access point, this access point here is in the same room with the Y-Spy, so there's definitely going to be no problems hearing it. You can see some shaping here. It's kind of a diagonal line. Now, unfortunately, Channelizer doesn't run that well whenever I'm recording on Cam Studio on this machine. This machine is only a single core. It does not have enough processing power to run Channelizer well and do the screen recording that I'm doing. So, instead, I'm getting a little more incomplete picture of what's going on. But for the purposes of this video, it is going to be good enough. But as you can see here, we've got kind of a diagonal pattern with a whole lot of gapping between things. So the signal usage is kind of sweeping through. And that is a behavior that goes along with Wi-Fi type networks. They don't just sit on one frequency. They're actually doing frequency hopping, just jumping around the spectrum. There are different ways that can be done. Some is through frequency hopping spread spectrum, and some is through direct sequence spread spectrum. If you want to see what those actually mean, I would recommend checking out Wikipedia or doing a Google search to find out more information about those. Not really important other than to say that instead of being a constant frequency, it is jumping around in frequencies, going through and doing its own sweeping, and that's how it actually carries the Wi-Fi data through the air. Now, on this screen, down here at the bottom, we have written out what the current frequency is for this column or whatever column we're working with. This column here represents 2.41 gigahertz, whereas this column represents 2.45 gigahertz. That's not really that useful whenever we're trying to use this for doing some looking around to see what Wi-Fi is in the area. So I'm going to change the labels for the x-axis right here to Wi-Fi. And now we have channel designations down here, 1 through 11. There are also 12, 13, and 14, but those channels aren't allowed for use in the US, so I'm not going to really touch on them that much. But we'll go ahead, and I'll just go ahead and tell you that my access point here, this one that's got a really strong signal, runs on channel 1. So I'm going to go ahead and click on 1. That highlights it. So you can see this expanse here represents channel 1. And you can see that almost all of that it is hearing is contained within that rectangle. Now there's a little bit out here, and it may just be because the Y-Spy is not a perfectly tuned piece of hardware, and it may be because my access point is not perfectly tuned. I don't have a more expensive spectrum analyzer, so I can't really tell you. I don't have access to a more expensive spectrum analyzer. Otherwise, I would love to show you the differences between this and what a lot of people in the industry would term as a real spectrum analyzer. Don't have those resources, so we're going to have to make do with what we've got. But just to show you, this is encompassed here with this channel 1 marker. Now my neighbor across the street runs his access point on channel 11. And as you can see, all of this traffic very well contained within the boundaries of channel 11. Now if I were coming in here and this was not my access point and this was not my access point, but I wanted to put an access point in, I would probably try to put it here into this empty area. I would look at these graphs, see, oh hey, this one's really strong. This one's, not really strong, but it's strong enough that I could use it. But this area here is pretty empty, so if I'm going to put a new access point in, I'm going to put it either on channel 6 or on channel 7 there, just based on the results of this graph. Now, it would not be a good idea for me to put it on channel 1. I could put it on channel 1, but since there's already somebody there, it's best for me to leave that alone and it's kind of one of those play fair kind of deals. I would be causing him interference, he would be causing me interference, so we're better off separating a little bit, and by separating, then we don't stomp all over one another. Another thing to watch out for is wireless video. Wireless video, or the cheap wireless security cameras that you can buy, the ones that operate on 2.4 gigahertz, actually probably all of them, but I've only ever seen what I'm about to show you in the case of 2.4 gigahertz. They're very noisy on the spectrum. I'm going to plug in one of the video cameras that I've got that is a wireless one. And as you can see, the red line down here went nuts. The blue area expanded considerably. And we have this very nasty area here where it is just very, very thick. Looks almost like a weather radar picture of something. That is what wireless video looks like to this unit. Wireless video is very, very noisy on the band. It just eats up. If this wireless video camera was over in my neighbor's house with his Wi-Fi operating where his Wi-Fi is operating, there is a good chance that you would not be able to use any kind of wireless networking at his house. You would not be able to talk to his access point. And it's simply because this is just eating up so much of that resource, just completely annihilating any hope of getting through. I'm going to go ahead and unplug that though, so that goes away and you can see that traveling through. Now I'm going to cut this a little bit shorter than what I had intended to originally. I've been fighting with Cam Studio and recording with the Channelizer software. This recording actually looks to be the first one that's gone well. So I'm probably going to go ahead and run with it, and I'm going to cut it shorter because I ran out of time to do it proper. But I will go ahead and go back over a little bit more about what it's really doing. So we're going to come back to what is going on, and then maybe show you a couple of the menu items, and then I'm going to have to end the segment. So it is shorter than what I would have liked, but just because of time constraints, I need to get this in so it can actually be put into the final rendering for the new episode of BSoD that's coming out. The new episode should be out within the next 3 days, and Fox needs to have some time to edit the final video, so I'm going to go ahead and try to get this ready for him. But I'll go ahead and show you some of the menus. So under Channelizer, you can get into Preferences. You can take an online survey that I've never taken. You can bring up the About screen that we had up earlier. Under View, you can open a recording. Now that's an interesting thing because in order to open a recording, you have to create a recording. And all you're doing when you create a recording is you are writing to a file what you are seeing here. This information is being written to a file. You can play that file back at any time later by just going File, Open Recording. So we'll create a new recording real quick. And I am going to name that recording myrecording.wsr. Yes, I wish to replace the old one that I did for a previous take. And now we're recording that stuff. I'm going to go ahead and plug in the camera here real quick. We're going to do a 5-second burst of this camera. So there comes up on our 5-second mark. And then I'm going to let it go for 5 seconds with the camera off. Then I'm going to plug the camera back in. Get another 5 seconds with the camera. Then I'm going to unplug again. And then I'm going to do that one more time. So we have a very distinctive pattern over here on this side that we're going to follow. Oops, I started up a little late. We'll go ahead and start it now though. So I have two 5-second bursts with a 5-second separation, and then another 5-second burst with a 10-second separation between these two. So it'll be really obvious whenever we go to look at this recording that is what we saw. So now I'm going to stop the recording, end recording, and now I'm going to play it back. So open the recording, myrecording.wsr, and here you can see the progress bar of playing back that recording, and here is all the data we captured during the recording. So we'll just go ahead and watch it here for a little bit. There's where we turned on the video camera for 5 seconds. You can see that. And then turned it off. So we are still following that pattern there. And then we turned it back on. And we'll just let that run for a little bit longer. And there is our last running of the video camera. So as you can see, we did definitely record it. We are playing it back in the time, according to the time in which it happened. And standard playback controls for any kind of a movie player applies here. We can jump to the end, we can fast forward, we can play, we can pause, we can jump back to the beginning. There are things like along those lines. This tells us when this was recorded, and this here tells us how far into the recording we are currently. So that mark there is 48 seconds into that recording. I'll go ahead and close that recording because we don't really need it anymore. But you could see from that recording that we did indeed have that pattern that I put in there of 5 seconds on, 5 seconds off, 5 seconds on, 10 seconds off, 5 seconds on for the wireless video. Now under the view, we can control what graphs we see. We can do the same thing with these marks here, these arrows that are in the corner of the graph's label. We can also change this down here. We can change it so instead of showing Wi-Fi channels, we show frequencies. We can do the same thing down here, back to Wi-Fi. And we can also show the Zigbee channels. I don't know anybody that has Zigbee. I don't have access to any Zigbee stuff. I've never seen any Zigbee stuff in my spectrum analyzing of anything. At least if I did, I didn't know I was looking at it. In my area, Zigbee's really not popular, so I never really used that particular label. I almost am always using the Wi-Fi label because anytime I'm using this thing, it's generally related to Wi-Fi, trying to track down problems or trying to put in new equipment. Also, you can clear out the views. I can clear the planar view, which is this graph down here. This graph kept all its data, but the planar view down here was reset. I can also clear everything, so it's like I'm starting over. Do I wish to clear? Yes, I do. So it clears the history and clears the planar view. They don't give you an option of just clearing the history, but to be honest, I don't know why you ever would want to. If you want to keep this but clear that, I can't think of a real scenario in which that would need to be something you'd want to do. So, well, this is the Channelizer software. This is version 2.0. This is for the Y-Spy hardware, and it is available at metageek.net. If you buy a Y-Spy, I highly recommend that the first thing you do is go download the updated software from them. The version of the software that came with mine was rather old and just absolutely horrible. They've made massive improvements here, so I would definitely recommend that you download the new software and run it instead. There is also software available for Linux and for the Mac. I believe they link to both, but they do not offer it. A third party has written each. If you've ever heard of software called Kismet, which is a Linux war driving software, the guy that writes Kismet also wrote a Y-Spy utility. I do not know the name of it, but he wrote a Y-Spy utility for use under Linux. And the other day in some random browsing, I actually came across a Mac OS X application for the Y-Spy. I do not remember the name of it, but I will try to track it down for the show notes. You can come on IRC and ask me, and I can track it down that way. Or it may be linked on MetaGeek's website. It's been a while since I went looking at their website. So, this has been Channelizer for the Y-Spy. I hope you enjoyed it. I hope you found it informative. If there is any other questions you have towards this software or towards the Y-Spy dongle itself, feel free to track me down on IRC. I use the nickname Ophidian, and I'm usually hanging out in the BSoD channel of irc.bsodtv.com. Thank you for watching.